Here's another important situation. We have a container which we assume is just sealed off. Nothing can get in or out. Let's say it's a rigid container so that the volume stays constant. It's sealed so that the number of moles stay constant. Pressure and temperature can vary. So let's say we've got some pressure P1 and T1 here, and we add thermal energy to the system. Then we get a pressure P2 and T2. Since we've added thermal energy, the molecules are moving faster, they have greater kinetic energy. That's where the energy goes. So the T2 is greater than T1. So we have greater temperature here than we had up here. Now since T2 is greater than T1, the added energy gives us greater molecular kinetic energy, which means molecules are moving faster. That means we have more frequent collisions, and the collisions are harder. The molecules are moving faster when they collide with the walls of the container. And both more frequent and harder collisions give us more pressure. If the collisions were just more frequent, we'd get more pressure. If the collisions were just harder, we'd get more pressure. The combination actually gives us a lot more pressure. In this situation, the pressure goes up with the temperature, so that the temperature ratio T2 over T1 turns out to be the same as the pressure ratio P2 over P1. These ratios are equal. There are several rearrangements we can make of this relationship. We could divide both sides by T2 to get P2 over T2, and then multiply by P1 to get P1 over T1 and get this relationship. Or we could do the reciprocal thing. We could get T2 equals T1 times P2 over P1. Or P2 equals P1 times T2 over T1. Okay? If we solve this relationship for P2, this is what we get. If we solve it for T2, this is what we get. And these allow you to do problems 15 and 16. 15, I believe, you solve for pressure given the two temperatures and the original pressure. In problem 16, you solve for the new temperature given the original temperature and the two pressures.